In this video, we're going to discuss matrices and the corresponding operations, starting with a definition of a matrix, which is defined as a set of numbers arranged in a rectangular array. And so we have a definition here that A equals a collection, so these small a values for all values of I and j, where I and j refer to a row and column respectively. So this example matrix that we have here on the right has m rows and n columns, with the last element being the mth row and the nth column. And there's a special case here, which we refer to as a square matrix, which occurs when m equals n, which we use quite often in doing things like solving systems of equations, which we'll get to in a later video. Now, in terms of the operations, one of the simplest operations that we can perform on a matrix is a transpose, which simply means we take the rows in the matrix and make them the columns, which in turn makes the columns the rows. This is defined here. A to the power t is how we indicate the transpose of A, which in terms of its indices means that every index that was ij now becomes ji. That's how we indicate the swapping of the row and the column. This might be clearer with an illustrative example. So let's take a simple matrix here, A, where we have 1, 2 in the first row, 3, 1 in the second. And the transpose of this matrix is simply going to be 1, 3, 2, 1. And you can clearly see that the first row previously is now the first column, the second row, second column, and so forth. Moving on to other operations, the next kind of step up in complexity are addition and subtraction. Now, matrices can be added and subtracted from one another, but only in the case where they are the same size. What we can see from these two operations, they're quite similar as one might expect, is that it's simply done on an element-wise basis. So if we look at the addition operation, we're simply looking at summing the corresponding positions in A and G to make S. And similarly, for the subtraction, we're taking the difference or subtracting the value G at a particular ij from the corresponding A value to get D. Now let's consider another illustrative example where we have two matrices, A and G. And so for the sum, for the addition of these two, we'll have a new matrix of the same size, because in this case they both have one row and two columns. And so it's simply adding up 2 plus 3 and 1 plus 2 to get 3. Then for the next example here in terms of subtraction, we'll start with the two same vectors A and G. This new matrix D, which is going to store the values of the difference, will have values 2 minus 3, which is -1, as well as 1 minus 2, which is also -1. And we can see here that we have, again, produced a matrix of the same size. And the note here is showing that if we were to try to perform the operations of A plus GT or A minus GT, these would not be defined, because even though they both have two elements, one is a kind of a row vector, the other is a column vector, and in these cases the shapes do not correspond, and therefore addition and subtraction of these two matrices would not be defined. And so the last example of a matrix operation that we'll be discussing in this video is going to be matrix multiplication. The first of which is scalar multiplication, where we're simply taking a constant value, in this case we'll refer to as beta, and we're going to multiply it times our matrix A. Here we can see that we can define this scalar multiplication simply by scaling each of the small a ij elements of A for all combinations of I and j. In terms of an example of this, we're going to go back to our matrix A, where we have 1, 2, 3, 1. And in this case, we're simply going to do the scalar multiplication of 5 times A, which should produce a new matrix of the same size and shape with values 5, 10, 15, and 5, representing 5 times 1, 2, 3, or 1. Our next and final operation for this video is going to be matrix multiplication. So another example of multiplication, but in this case, we're going to be multiplying two matrices together as shown here for the example of C equals AB. What you have to be particularly careful with for matrix multiplication is that this operation is only valid in the case that the number of columns in the first matrix equals the number of rows in the second. As we look at the definition of the small c, so the elements of that product of A and B, we can see that we're summing along J, which in the case of A will move us along a row or across the different columns, where for B, J is going to move us down a corresponding column, meaning moving across the different rows. And so that's why in order for this to be valid, we have to have the same number of rows in the second one as we do columns in the first. And again, an example often makes this more clear. B in this case is simply the value is 2, 2. And so we could define this product C as A times B. So based off of moving along the first row in A and down the column in B, at each corresponding position, we will simply multiply those numbers, ultimately adding them together. So we have 2 times 1 plus 2 times 2, which is going to be 6 for the first value of C. And then looking at moving along the second row in A and the column in B, we're going to end up with 3 times 2 is 6 plus another 2 for a total of 8. So in multiplying A times B to produce C, we end up with a column vector. So it has 2 rows, 1 column with values of 6 and 8. So one way of trying to visualize whether or not a given operation would be defined based off of the dimensions of two matrices is to kind of write out the dimensions next to each other, and the inside dimensions must match in order for it to be valid. So if we consider the case of AB, which we just computed, we see that we have a 2 by 2 matrix multiplied by a 2 by 1 matrix, which ultimately is defined. We'll say this one is okay. For the case of A times B transpose, now we have a 2 by 2 times a 1 by 2 because we've taken the column vector and made it a row vector. And we can see if we consider that inside dimensions, as indicated by that little half circle there, this would not be defined because those two numbers do not match. Lastly, in discussing multiplication, I want to mention the special case of an identity matrix, because for most operations, A times B is not going to be equal to B times A, but the only situation where that is going to be true is when one of the two matrices is the identity matrix. And so as we can see here, the definition of an identity matrix I is one where you can multiply it times the matrix A, or A times that matrix, and what you'll get in return is A itself. Looking at an example here, we can see for the 2 by 2 case that the corresponding identity matrix is going to be of the same shape as A, where we have 1s along the diagonal, 0s elsewhere. And that's the case no matter how large of an identity matrix we're trying to produce. So the identity matrix is going to be a square matrix, 2 by 2, 3 by 3, and so forth, where you're always going to have 1s along the diagonal, the major diagonal, so starting in the top left corner, going to the bottom right, with 0s elsewhere. And looking at the multiplication of these two, if we worked across the first row and down the first column, you should end up with a value of 1, then 2, then 3, then 1, showing that taking A, multiplying it by this example of an identity matrix produces A, as is expected based off the definition. That concludes this video on matrices and matrix operations. Future videos will discuss how matrices and their operations can be useful in performing tasks such as solving systems of linear equations.